Okay, it's time to look at some examples of efficiency problems. These are very straightforward overall. So just go through a couple of them, and then in the next video we'll look at some more advanced problems. So what I have here, I've got a water pump, and the water pump, what it's doing is it looks like it's pumping water up a 45-meter tall tower. So we're gonna have some kind of tower here and draw a sketch of the situation. Here's my tower, and at the top you have a big tank of water, okay? And then what's happening here, we're lifting the water up, and it's going to have a height of 45 meters. It's a very high water tower. Okay, here we go. And we know we're lifting up 3.2 kilograms. 3.2 kilograms. And what we're doing is we're lifting the water up. That's the desired form of energy. This is going to be my output energy, and it's going to be my gravitational energy. It's output. There you go. So output. Now, where's the energy coming from that's going into the system? Well, it's going to be from the pump. Now, what do we know is this? We know the power of the pump. It's going to be usually at the bottom over here. So I'm sketching it over here. And I also know that we're pumping this many kilograms every second. So we have a time over here. It's kind of hidden, but it's there. Now remember, this quantity is an exact quantity because it's written out. So we're going to assume an infinite number of significant digits here. So just something to keep in mind. And what we can do is something cool. I need to get energy from this. So I need to get energy, and that's going to be my input energy. Now remember, the power equation is equal to the change in energy over time. Well, I can use this equation to determine energy. I just simply rearrange the equation. So the energy is equal to power times time. And I'm going to call this energy from power. It's not proper, but that's okay. We'll use that label for now. So energy from power is going to be my input energy. Well, let's look at how we solve this now. Well, for percent efficiency, what we know is that it's the ratio of the output to input energy. There's our little formula here. And I know that my output is going to be my EG. And then my input is going to be energy from power. Then all we have to do, we substitute a little bit over here. Won't take very long. So mgh all over power times time. And we're going to substitute a little bit further, and then very quickly we'll end up with the following. I'm just going to jump ahead to the next slide here just to show you. We're going to end up with 1,413 joules from power, or from EG. That's how much energy we get out. We put in 1,500 joules from the power energy equation. So it gives me an efficiency of 94%. Okay? So just to save a little bit of time, I just jumped the gun up. Okay, here's another question. This one involves a pumpkin. Now this pumpkin is going to be dragged up along a ramp, it looks like. So let's label everything here. So I'm going to be dragging, maybe make it like this. There you go. Dragging a pumpkin up this ramp. So let's use a little orange color over here. Draw a little pumpkin. There you go. There's my little pumpkin. Okay. And the pumpkin is being lifted upwards. So it's going to gain a height of 2.5 meters. That's the whole idea behind a ramp. You want to lift something up. So it's going to have a height of 2.5 meters. So it's going to gain gravitational energy, potential energy. So that's the whole purpose here. That's going to be my output energy. Well, where's this energy coming from? It looks like we're exerting a force over here. So I'm pushing this pumpkin with a force of 588 newtons, and we're going to be assuming that this force is going to be exerted over the entire 5 meters of the ramp. So what does that mean? That's right. It's going to be work energy. So your energy from work is going to be your input energy here. So let's look at our energy conservation equation. Here we go. So it's going to be equal to your output over input, just like before, times 100%. So your output is going to be your EG. Your input is going to be your work energy. And now let's put in our equations. So percent efficiency is mgh all over force applied times your displacement for work by 100%. Substitute some values in here. So we're going to have our mass, which is 75 kilograms, 9.81 meters per second squared. You get the idea. We're lifting the pumpkin up 2.5 meters. And then this is all over 588 joules, or sorry, newtons. So we're pushing with 588 newtons of force. And this is exerted over the whole 5-meter length of the ramp. And what do we end up with? So for the EG, looks like we're going to have 1839 joules of EG. And this is all going to be over, let's calculate this, 2,940 joules of energy that we put in by the work. And once you calculate this, you end up with 0.625 or 62.5% efficiency. Now, with significant digits, let's look at this. It looks like we've got 2 overall. So we got to do a little bit of rounding here. I don't think I was exactly 62.5, a little bit higher. So therefore, the ramp was 63% efficient. So that's it. These are fairly straightforward problems. So what you need to really be careful with these is do not mix up the input and the output energy. The output's always the smaller energies. If you can't identify them, look for the smaller type of energy. And that's going to be your output. You always have to put more energy in at the beginning. So that's it. Okay, there'll be some more advanced problems for you to try out. Hopefully you do well with them.